Welcome to Math Shorts, tantalizing mathematical tidbits that will amaze, entertain, and delight. Math Shorts is brought to you by the Ottawa Zone for Mathematics Education. The Ottawa Zone for Mathematics Education is a chapter of the Ontario Association for Mathematics Education. Information about both organizations can be found in the information for this video. In this episode of Math Shorts, we're going to explore a number trick. I encourage you to work along with the video. You're going to need to do some computations, so get yourself a calculator or some scrap paper for doing your calculations. Be ready to pause the video to allow yourself time to do these computations. Pause the video now if you need time to get your materials ready. Okay, here we go. I want you to pick a two-digit number where the two digits are different. So something like 57 is great, but something like 33 is not. Do you have your number? Okay, I want you to switch the order of the digits to make a new number. So if you had something like 94 was your number, you'd switch the digits and get 49. Now, I want you to find the difference between the two numbers, the original number and the switched number. So you're going to subtract the smaller number from the larger number. Once you've got the answer to that, I want you to add the digits of your result. So after you did the subtraction, if you got 67, you would do 6 plus 7, which is 13. Now, when you have your answer, this is a secret. Don't tell anybody. But I want you to concentrate on that answer really, really hard. Okay, you must be wondering, how did I do it? Take some time to think about this. Try out some other examples. See if you can see a pattern. Most of you are going to be able to see what's happening. But the most important question is, why is this happening? This is a much harder question. Don't get frustrated if you can't determine why this is happening, but take some time to figure out as much as you can before you continue and I show you the answer. Pause the video at this moment and explore this problem. Did you figure out what's going on? Let's explore the problem together. When you're trying to solve a problem and you don't know what to do, a good strategy is to play around with the problem. Sometimes, when you do this, you're going to see something that's going to give you an idea that you might not have thought of otherwise. Let's start our exploration by working through a couple of examples. So, suppose we had picked 57. We would switch the digits to get 75. We would subtract 57 from 75 to get 18. We'd add 1 plus 8 to get 9. Just as I predicted. Let's try another example. If we started with 91, we'd switch the digits to get 19. We take the difference between 91 and 19, which is 72. And 7 plus 2 is again 9. It seems that in both of our examples, we get 9. You may wonder, do we always get 9? If we always get 9, it'd be pretty easy for me to predict the number, wouldn't it? Let's look at it a little bit closer and see what's happening. So, suppose we started with 57. We know from our place value system that this really means 5 10s and 7 1s. we can write this in mathematical notation as 5 times 10 plus 7. Similarly, at our next step, when we write 57 and switch the digits to get 75, 75 is 7 times 10 plus 5. So let's go through our computations, but we'll use this expanded notation. So the difference between 75 and 57 is going to be the difference between these two expressions. Now, we can use a little bit of algebra and drop our brackets, keeping in mind that we're subtracting everything in the second bracket, so it's going to be minus 5 times 10 and minus this 7 as well. And now, if we look closer, we see that there's going to be a couple of terms that actually have a times 10. And we can group these things together. We've got a 7 times 10 and a minus 5 times 10, so I can rewrite that as 7 minus 5 times 10. Now, if you've done any factoring, you know it'd be nice if the other part had a 7 minus 5 as well. And if we looked at the leftover stuff, there are some 7s and 5s, but unfortunately, it's minus 7 and plus 5. But we can just rewrite that as minus 7 minus 5. Because I'm subtracting everything, I'm going to be minus 7, which is that, and minus 5, which is going to give us our plus 5. Now we have a common factor of 7 minus 5 in both terms. What's left over? We've got a 10 from the first term and a minus 1 from the second term. So that gives us 2 times 9, which is 18, and 1 plus 8 is our 9. Okay, let's look at our second example. If we did 91, and again we wrote it in this expanded format, as well as 19 when we reverse things, then when we do the difference, if we go through exactly the same process of subtracting these two expressions, bringing together the stuff that is the same, factoring it, we end up with 8 times 9. So again, we're getting something times 9. 72, 7 and 2 is 9. So again, we're starting to see another pattern. When we go through this process, we're always seem to be getting a multiple of 9. How can we be sure? It might just be the two cases that I looked at. So let's do something a little bit abstract. So we'll do the general case where this AB, I'm really talking about a two-digit number where A is the tens digit and B is the ones digit. So we write that as 10 times A plus B. We'll assume for now that A is bigger than B. It doesn't make a difference, it's just when we go to do our subtraction, we would write things the other way. So when we do our reverse digits, that's B times 10 plus A. We'll do our subtraction exactly the same as our numerical examples and get rid of our brackets, gather our like terms. We get that common factor of A minus B times 10 minus 1, which is A minus B times 9. Okay, so now we end up with a product of 9 and the difference of the digits. So what's so special about these multiples of 9? Well, let's take a look at them. 1 times 9 is 9, and obviously if we got 9 as an answer, the sum of our digits would just be 9, and it would work. 9 times 2 is 18, 1 and 8 is 9, so it works as well. 3 times 9 is 27, 2 and 7 is 9, so it works as well. Now, if we look back to our second last step, that 9 actually came from this 10 minus 1. So another way to think of 9 is 10 minus 1. So when I go from 1 times 9 to 2 times 9, I'm actually adding 9 to it, which is the same as adding 10 and subtracting 1. What does that do to our number? Well, it makes our 10 digits go up by 1, and it makes our units digit go down by 1. So here I had 0 tens and 9 ones. Now it goes to 1 10 and 8 ones. This goes up by 1, this goes down by 1. I go down the list, I'm going to have the 1 goes up to a 2, the 8 goes down to a 7. What does that mean for the sum of our digits? Well, if this guy's going up by 1 and this guy's going down by 1, we're going to end up with exactly the same sum down here. Because, yeah, this will be 1 bigger, this will be 1 smaller. It's the same as doing 1 plus 8 plus 1 minus 1. And that 1 minus 1 isn't going to make a difference. So all the way down, we're getting exactly the same thing. And that's why our trick is going to work.
The idea behind our number trick is also related to the principle behind the trick for doing the 9 times table with your fingers. For example, if we wanted to do 7 times 9, we would count off 7 on our fingers. 1, 2, 3, 4, 5, 6, 7. Put down the 7th finger. If I count on the one side, I have 6 fingers. If I look at the other side, I've got 3 fingers. So my answer is 63.
For a mathematician, in many cases, answering a question is just the beginning of their work. Along the way, and at the end, it's natural for some questions to come to mind. For example, in our case, does this trick only work with 2-digit numbers? Get into the habit of asking yourself questions, then try to answer them. There's a whole world of interesting stuff going on behind this one little number trick. Take some time to explore, and you never know what you're going to find. I hope you've enjoyed this episode of Math Shorts. Check the channel out next month for our next episode. Until next time, keep thinking.